Welcome. This is the third video in the series on Principles of Radiographic Exposure 2. In this video, we will explore computed radiography. We will look at the components involved, the physics of image storage and capture, and the processing of the image. Also, as a comparison, a brief lesson on screen film radiography. We will discuss CR image properties, sources of noise, and radiation dose. If you haven't watched the first two videos in this series, I recommend you do it now. Let's get started with history and background. Many advances in imaging and computer technology took place from the first electronic computers in the 1950s to the 1980s. In the 1980s, computer technology advanced to the point where a single system could take in data from a source, process it, manipulate it, correct for errors, arrange the new information on a grid called a matrix, and display it as an image on a display. This technology was adopted and refined for use in radiology, and so by 1981, the first CR system was developed by Fuji and was available for purchase and install in departments. We'll go ahead and we'll take a look at the film screen process as it has similarities to computer radiography. So in screen film radiology, the intensifying screen emits light in response to X-ray interaction. So this is the cassette. There's a physical film that would capture the image, and the intensifying screen, which is what this was made of phosphors, and it would actually emit light, and the light would expose the film. The light exposes the film, which now has the information on it. This is called the latent image. So the latent image would be on the film until it was processed. The film was processed through traditional photo processing techniques, and then the image would be visible. This process has similarities to computer radiography. In computer radiography, the image information is stored in a latent form and then processed later to create the final image. This would be an example of an automatic processor where the film goes in and all the steps are taken care of and the film would come out here. This would be a hand washing or by hand process. Now we'll go ahead and we'll talk about the cassette and the plate in CR. The cassette does not have to be light tight as it would in film radiography. The cassette can be made from plastics or metals. Aluminum is often used. The cassette can be opened, and inside will contain the plate, which can be exposed to light. If the film was exposed to light, it would be useless. It would like fog it out, we would say. The plate of the cassette will have a soft felt-like material to protect the plate and reduce static buildups. And here's some pictures of the cassette. So these are two different types. This is Kodak, this is Agfa, and this is the inside with the, you could say, image plate. We'll learn that it could be called a PSP. But this is what would actually receive the X-rays, and where the information would be stored would be on this plate. So we'll go ahead and we'll look at the plate and their components, their parts, and their function. There's a protective layer, which is a thin, tough, it protects the phosphor layer below it. The phosphor layer contains the PSP that traps electrons during the exposure. The support layer, which is a semi-rigid layer, gives the imaging sheet some strength. Then the conductive layer absorbs and reduces static electricity. Next, the light shield reflective layer sends light in the forward direction when it's released in the cassette reader, and we'll get into how that's done. The color layer, which on some of the newer plates absorbs stimulating light but reflects emitting light. So we'll learn about the different types of light, and there's an added layer that could be in here called the color layer on newer type plates. The backing layer is a soft polymer. It protects the back of the plate. So that image plate that we looked at, those would be the different layers that makes it up. We'll talk about the PSP. The barium fluorohalide compounds like barium fluorobromide and barium fluorochloride are utilized to create the photostimulable phosphor. So the PSP is the photostimulable phosphor. These compounds are doped with europium to increase their effectiveness. So the compounds used would have these chemical forms. And there's many other different types. These were the more common ones used, but there were roughly a dozen plus different chemicals that could be used. It was always doped with something, usually europium. These materials are used because they have special properties called stimulated phosphorescence. Phosphorescence, this means delayed emission of light. Phosphorescence is delayed emission of light. Stimulated is when there's an energy put into it. Okay, and we'll learn about what that energy is in the next slides here. Sometimes the plates are called SPSs, which would be storage phosphor screens. That would also be what they may be called in some texts. Let's look at CR image formation. So the CR exam cycle, the plate's exposed, it's processed, and then the image is displayed. So this is a process. So image formation is the step on the left. So image formation is happening when the x-rays are being created and the patient's being exposed. Okay, and the plate should be here, hopefully, and it's receiving those x-rays. The CR exposure. In CR, the x-rays in the remnant beam interact with the plate inside the cassette. Inside the phosphor layer, a response occurs that energizes the electrons. So once the phosphor layer is exposed, or the incoming x-rays come into the phosphor layer, a response occurs in the electrons, trapping them in a temporarily higher state. When that happens, as with the photoelectric effect, the atom needs to give off energy that it has gained. It does this with the release of light. So as the plate's being exposed, it will actually luminesce. It will actually give off light, which is luminesce, as opposed to phosphoresce, which is the delayed giving off of light. That will be important later. Now, when X-rays expose the plate, half the electrons in the PSP return to their stable state immediately. The other half remain in that excited state, which could also be called metastable state. These excited electrons are the image data on the CR plate. So the position of the electrons, how excited they are, that is the image on the plate, which we would call the latent image. So the latent image is in this form. The electrons can remain in this higher energy state for some time, which is an advantage because the plate does not need to be processed immediately. After about 8 hours, about 75% of the original data will still be maintained. The excited electrons enter a state where they have a higher energy than usual, but have not been released from the atom, which we call ionization. the usual state of the electron is known as the ground state. So we can see the ground state here, and as depending on how much energy, how much energized the electrons become, they can be in different excited states. And once they've received so much energy, they become ionized. We learned about this in interactions with matter in Principles of Exposure 1. If you haven't watched that video, I recommend you do it now. The electron can have multiple states, as we talked about, of excitation depending on the atom and which shell the electron started in. There's a concept called an F center, which has to do with the phosphor. It can be described that the excited electrons are in the F centers of the crystal lattice of the phosphor. So this would be a lattice. This only happens to a small percentage of exposed atoms in the phosphor. So this would be the lattice here of the barium with the europium in it, and there will be spots that we call holes in physics. Is called electron holes, which is like a positive area. So the negative electron, once it gets excited, it can fill that hole, which is known as the F center. Through computer and image processing technologies, a small amount of the electrons that will enter the higher state are enough for the CR processor to create the final radiographic image. We'll go ahead and we'll look at two different aspects of the same thing. With europium as a doping agent and barium fluorohalide, there is an F center, which is a hole, as we talked about, that the electron can be excited and enter into, and still in the atom's influence. So we see here this is looking at the same exact thing. It's just two different concepts of physics, I guess to say, but it's actually the same. It's actually the same thing. Okay, so you have the valence shell, which is the outermost shell, and then the free floating, which can also be called the conductive band, which would be the ionization state of the electron. Metastable in the F center, the excited and energized electrons are all in the same state. It actually has to do with electron spin states and all this stuff, but we don't need to get into that. We just need to know that these terms may be used to describe the electron in the plate after exposure to X-rays and before the processing. They are the same as we talked about in the excited state model is more accurate. So this model can be more accurate for visualization of this. The F center, this would be like the lattice of the phosphor, and there's a center here that the electron can still be in the influence of the atom, but also but be stuck in this state. Okay, both of these are showing the same thing, is the point. But both these terms could be used to describe this metastable state. We'll talk about CR processing. Let's take a look at the CR exam cycle once again. Processing is the middle step right here. There are 3 steps in the processing of the image. It includes stimulation, read, and erase. First, we'll take a slight step back here and we'll talk about the crystals and the phosphors a bit more. We've mentioned those terms, but we haven't really talked about necessarily what they are. A crystal or crystalline structure is a solid material whose arrangement is a highly ordered microscopic structure. The crystal extends in all directions and it forms a lattice, and this would be examples of a lattice. Okay, it's a uniform shaping. Okay, and the atoms are actually formed in a uniform way, okay, and that's how the F centers are created. Like it would be in between these areas, okay, and it extends in all directions. A phosphor is a substance that inhibits a property that exhibits a property called luminescence. So phosphor is just a substance that exhibits a property called luminescence, and we learned that luminescence is anything that gives off light, right? So this is a crystal, okay, and it has a structure of a lattice. So that's the two different things, between a crystal and a phosphor. The electrons in the excited state is the latent image on the image, as we learned about. So the first part of the CR processing is stimulate. The latent image is released, read, and processed for display. The plate is scanned with a laser directed at a polygon or mirror that is oscillating. The laser is then directed through a waveguide or wave shaping process. This is necessary to create a thin beam that will stimulate the plate. This finely focused beam of infrared light, which is a laser, has a diameter of about 70 micrometers typically, 70, 80 depending on the system. The laser is monochromatic, and this means that it's comprised of only one wavelength. The diameter of the laser beam determines the spatial resolution as well as how fast, which we'll learn about later, how fast the motor moves the plate through. CR processing, so the read step, so we had stimulate, read. As the plate is stimulated, the high energy state electrons are knocked down to the ground state, so the energy is released from the excited electrons, and as with the photoelectric effect, light is released. The releasing of light is guided through a light channeling guide and to a photomultiplier tube, which is a PMT. Very little light is released in this step. The signal, which is the light being released during this read step of the CR plate processing, is increased in this step. The photomultiplier tube increases the light. So photo could mean light, or it could just be anything of the electromagnetic spectrum, really. But photo is like a photon. Multiplier means to multiply together. Okay, and tube is the device it is. Okay, so photomultiplier. So in this step, the light is increased. The signal is then digitized by an analog to digital converter, and it's sent to the computer for processing. The light that is emitted from the plate is emitted through a process called the PSL process, which is photostimulable luminescence. Is when a different light source, like a laser, is applied to the plate, and the PSP emits light. And this is the act of it right here. This is a picture of it. So the energy is stored in those higher state electrons inside the PSP, inside the plate. The light, the laser inside the CR reader releases that energy. It knocks them down to the ground state. Energy is released in the form of light, and that process is known as the PSL process, photostimulable luminescence. Okay. The emitted light from the image plate is polychromatic. That means it has many different shades. It's, to the eye, it would look blue, whereas the laser is monochromatic. It's only one frequency of light. the laser and the emitted light are many orders of magnitude different, so the laser light and the emitted light can be distinguished from one another. And here's a picture of what it looks like. So there could be two different types of lasers that's used. The helium neon gas laser, solid state laser would be these two frequencies, and you see they're one solid line for their emission spectrum because there's only one frequency that they are. There's a large gap in between here, and then the emitted light is here, and it's polychromatic, so it has many different frequencies within it, but there's a large difference between the two. So the optics and the electronics are focused on only looking at this light, and so the laser won't add noise or will disturb the acquisition process of the information, which is just the light being emitted off of the image plate. Since we've been throwing a few terms around, let's go ahead and we'll define them here, and we'll kind of cement them in on what we've been talking about. Luminescence is any emission of light from a source or an object. Fluorescence is the immediate emission of light under a stimulation, which that could be X-rays, or it could be laser, or it could be a light source. Fluorescence is the delayed emission of light after the original stimulus, so something that would be like phosphorescent would be something that's glow in the dark. So if you have a glow in the dark phone case or badge or whatever it happens to be, you put it under light, so it's received a stimulus from the light, and then you put it in dark, and now it's emitting light itself. So that's the delayed emission of light after the original stimulus is phosphorescence. Stimulated phosphorescence is the delayed emission of light with a re-stimulation after the original stimulus. So for CR, the laser stimulus is the stimulus, and stimulated phosphorescence, it's the laser inside the reader is the re-stimulated part. The original stimulus is the original X-ray exposure. So the CR plate, the image plate in CR, undergoes stimulated phosphorescence as it's being read. We'll go ahead and we'll look at this picture once again. We're talking about the image display step on the right. Image display. The computer will now perform image processing operations and will display the image. Image operations is a robust subject and will be explored in later videos. After simulation, some of the electrons will remain in a higher state. An intense white light is utilized in order to put electrons back into their stable state and remove the latent image. So any electrons that didn't get knocked back down by the laser, an intense white light will be used, and this is called the erase step. The cassette is now ejected from the reader and is ready to be used again. So we have this nice picture here of the CR processing steps. We start with it being exposed during the exam, and then the stimulating lasers used inside the CR reader. To stimulate, light is emitted, and it is read by the PMTs. It's collected, the photomultiplier tubes. It's sent off to be digitized by the analog to digital converter, and then it's erased with an intense white light, and then it's ready to be used again in another exam. Now we've talked about the process for what happens when the plate's exposed to X-rays how the plate is processed, how it's read. With stimulation, it's read, the light is picked up, and then it's displayed on the image. It's erased, the plate, and it's displayed on the image display. Now let's talk about the CR reader at this point. The CR reader, which is seen here, consists of mechanical parts, optical parts, and computer parts. These are different types of systems here. This would be like an AGFA, and this is Kirschring, which is Kodak. This is like a multi-reader style, where you can put multiple films in here. Mechanical aspects. Each manufacturer can have different configurations and implementations for the CR reader, so there may be slight variations in the materials used, how it's used, and things like that from manufacturer to manufacturer. But mechanical, the image plate is removed from the cassette. This is performed with suction cups. So when the image plate goes into the reader, or it sits on top of the reader, and sometimes the image plate, the cassette is opened by mechanical means, and then the image plate's removed from the cassette. By suction cups, the plate is then guided through rollers and is driven with a motor at a precise speed. The motor must be a constant speed or banding will occur. So if the motor doesn't move at the correct speed, it will be a mismatch of information because it's expecting that the information that it's reading at a certain time is at that point in the image. So it's taking that data and it's going to put it in those spaces on the matrix that it's making up of the image. And if it's not, if it moves too fast at some point, the data is going to be mismatched. Okay, and an effect called banding can occur. An oscillating mirror deflects the laser back and forth on the image plate that we talked about earlier. There's optical components. There's the laser, which is shaped to the correct size and focused to the plate through the mirror and or a waveguide system. There are light collecting optics that are typically thin tubes of glass. They could be known as fiber optics. There could also be a lens type device that's used, but it's typically fiber optics. Optical filters, which filter out the stimulating light and improve signal to noise ratio and contrast to noise ratio. So the stimulating light and the emitted light, right, even though they're very far apart, as we talked about, there's still a filter in place to even make this process better. The photomultiplier tube, which takes the low-level signals of light incoming from the collecting optics and increases them. There's photodetector at the end of the photomultiplier tube, which merely just detects what's been amplified, the signal that's been amplified, the light signal, and it will convert the light to an analog electrical signal. Then there's right after that, there's an analog to digital converter. There may be other electronics in between, but there's an analog to digital converter, and then the digital signal can be sent to the computer. The computer works digitally. It doesn't necessarily understand analog signals at all. The computer. The output of the photodiode is processed for amplitude, scale, and compression. The signal is shaped before the final image is formed. Then the signal is digitized. An analog to digital converter is used to do this, as we talked about. So these steps are done before the computer. The control system for this works off the computer's clock speed. So the clock speed typically will be the processor speed, 2.4 gigahertz is what we would say, and that controls the clock speed controls the system. Image processing operations are performed. Then this image is then displayed on the system monitor for viewing and post-processing manipulation by the radiographer. And as we said, these steps there's a lot to it, and later videos will go over these processes. We talked about all these components, the mechanical components, optical components, the computer. We also talked about the process so far of the stimulate, read, and erase. Let's go ahead and look at it and put it together all in one picture here. So the laser beam comes in. There's an optical scanner, it says, which would be like the polygonal mirror that's oscillating, okay? And that's gonna direct, and there could be other components in here, but that's gonna direct the laser beam down at the imaging plate, okay? And it's gonna make a type of fan beam, it could, or it's gonna sweep it back and forth across the imaging plate. The imaging plate's gonna move, it says in this picture, in this direction by the motor. It's gonna move at a very constant speed. As it's being read, the information on the image plate, which is just a faint blue light, okay, is gonna be released by PSL, the photostimulable luminescence, and that's going to be collected by the collecting optics, which is going to be the fiber optics, very thin tubes of glass. That's going to be directed at the photomultiplier tube, and here there's going to be a filter also. So this light is typically very red, the laser. This light's typically very blue. The laser light is monochromatic. The stimulated light is polychromatic, many different shades, which is good because that's what we want, because that's going to make up more information for the image. Okay, and then here there's going to be a photo detector, which is going to detect the photons, which the light that has been multiplied by the PMT, and then that's going to be sent here. There's going to be some other steps that could be involved right in here for shaping the signal, the analog signal. Then it's going to be converted to a digital signal. And as we learned in earlier videos, digital signals are discrete. So it's discrete lines. It's on a complete waveform, like the light is. And then that can be sent to the computer for all the processing operations. So we've talked about the CR processing steps. We've talked about the stimulation step of the CR reader. We've talked about the read step, and we've talked about the erasure step. We've also talked about the CR reader itself, some of the mechanics involved, the optics involved, and the computer parts involved. Let's go ahead and let's see it in action. So we already have a set that's been exposed. We're going to flash it under an exam. This puts the patient information on it. It also says what exam and what image is being done. This is going to change how the computer processes the image data through algorithms. We'll talk about that in later videos. Like I said, it's going to go in. It's going to open up here. Suction cups are going to come in and take the image plate and bring it down to the laser in the motor apparatus. We'll hear the laser here in 1 second. Here it is. It's going to move at a very steady pace. The laser light's going to stimulate the electrons, and then, which is a red light, and then it's going to release through the PSL process blue light. That blue light's going to be picked up by the collecting optics. It's going to go to the photomultiplier tube, photodiode, and then the analog to digital converter, then to the computer. At this step, it's the erasure process, the very white light that we can see clearly here. It's going to erase the image plate. The suction cups, once it starts moving, it's going to take the IR, the PSP, the image plate, all those things. It's going to put it back in the cassette, as we saw right there. The cassette's going to close. It's then going to be ejected, and it can be used again. We'll go ahead and we'll see the windowing and leveling once the image is being displayed on this phantom skull. A cell phone, scissors, paperclip. So we can manipulate the image with post-processing techniques. Windowing and leveling is the most basic, where we can change the contrast and change the brightness. We'll go ahead and we'll move on to the image properties now. For CR, the spatial resolution is controlled by the read pitch of the CR reader. The pitch is the thickness of a single read line by the speed of the reader. We needed the laser to be very thin, is what we said. So this is the thickness of the read line, is how thick the laser is. And the speed is how fast the image plate's going in the direction of the read by the motor. The equation for spatial resolution is 1/2 times the pitch. For smaller plate size, the resolution is typically greater. So we can see that the spatial resolution is controlled by the thickness of the laser, because that's part of the pitch, and also how fast the motor moves. The smaller plates, the resolution is going to be greater. And we'll go ahead and we'll continue talking about CR image properties. In computer radiography, the bit depth is typically 14, which would be 2 to the 14, which equals about 16,000 different gray values. In film, it's about 30, the screen film process. The spatial resolution of a CR system is 5 to 7 line pairs per millimeter. For film, it's typically about 7 line pairs or 5 line pairs per millimeter. In CR image, the image is quantized. Therefore, pre and post processing manipulations are possible, including the window leveling, which we saw in the last video there, masking, and algorithmic changes. We can reprocess the image completely to highlight different things. And that's completely not possible in film, of course. Contrast can be the same over a wide variety of ranges. In film, contrast is highly dependent on the exposure that was used. Principal source of noise is scatter regardless of the IR used, regardless if it's a digital detector, which we'll talk about in the next video, if it's a CR image plate, the PSP, or if it's a film in the film screen process. Scatter is a principal source of noise. This is a reminder of the scatter process. CR plates are 10 times more sensitive than film to accumulated background radiation. So this is going to cause more noise on the image, other sources of radiation that may expose the film, or just being in the room and receiving possible low doses of the radiation as you're making other exposures to the film. CR noise sources are bothersome at low IR exposures. So when the image receptor has a low exposure, you use a very low technique. The noise sources become more bothersome. When low technique is used in computer radiography, it has decreased signal to noise levels. So the signal becomes much less, the noise becomes much more. Some sources of the noise, other than scatter during the exposure, is a slower fast scan drive. It can be a mechanical defect. It can be a source of noise. Motor driven at inconsistent speed. Optical defects can include laser intensity control. The laser being too high or low can cause the stimulation to be different in different places, especially if it varies within a read cycle. Scatter of stimulating light, so the stimulating light not being collected properly by the collecting optics. Computer defects can include electronic noise from the ADC to the through the wires and inside the computer itself. There could be electronic noises that get added to the signal, inadequate sampling, inadequate quantization where there's a low signal so it doesn't get enough data in those areas. Patient radiation dose in CR. Images can be made at low mass and higher KVP, resulting in a lower dose. So we can use less quantity of radiation. A low IR exposure can cause an increase in noise, as we talked about. Fewer repeats exams due to the wide latitude. So a image plate, CR image plate, has a wide latitude that can be used for acquisition of the image. This means that a wider range of exposures, techniques that can still result in images that have acceptable contrast and brightness. IR response function CR extends from 0 to 3 orders of magnitude, which is a range of like 1,000 times. And here's a picture of it compared to film. So the exposure is down here. This would be what we set at the console, and what is actually reaching the film, either the film or the CR plate, right? So the exposure for film, this is the only usable section. Everything here just becomes completely dark because it's being overexposed. So everything here, all the anatomy would become completely dark. Right here, all the anatomy here would be completely white. So the acceptable range of exposure is only from about here to here. So that's about 10 orders of magnitude here, 0.1 to 1 it says for this example on this graph. Here, everything too low would be useless. That would be the low signal problem that we talked about that it would run into, where not enough electrons were stimulated in the film, so when it's trying to read it, there's not enough information to grab to make an image. And then everything up here would be considered underexposed, but it could still be an acceptable image. Correctly exposed would be in this area. Overexposed would be in this area where we use too much radiation, perhaps, but it's still going to produce a acceptable image. And then everything beyond that at a certain point is going to be useless. So this curve right here, how it flattens out the dotted line here, everything here, everything's going to be black. It's going to be hard to see anatomy at this point. So that's what this curve is showing here. So for the plate, it can go even below an exposure. Okay, it may be underexposed, but it could still be acceptable image. So we can use less exposure here. We would like to be right in here, in this area, where we're using less radiation, so to say, for the exposure than what a film would do, but we're still producing an acceptable image. Okay, and we can also overexpose by quite a bit. So this is the exposure latitude. So latitude means how far one way or the other you can go, and this is showing that in our technique for CR, we can go very far down and very far up, and we can still have acceptable images, which would be from here to here. Let's go over some pros and cons of computer radiography. Some pros are that CR has a wide latitude, as we just talked about, the exposure latitude. No chemicals or physical film is used. It's easy integration into packs as it's already in a digital format. Digital pre- and post-processing image manipulation is possible. Can be used with already installed rooms, so you can buy the plates and the reader, and you can use a film screen room. With it, exposure made at higher KVP and lower mass can result in lower patient dose. Some cons of computer radiography is that it's more sensitive than film to accumulated background radiation. The initial cost for the install to buy the equipment compared to just keeping the film that a room may have. A ghosting artifact is possible. A ghosting artifact is where all the electrons weren't knocked down in the PSP from the erasure process from a previous read cycle, and now there's still image data left on the film. You go and you take another picture, you reprocess it in the reader, and now there's another image being displayed. It may be very faint, but there's still anatomy from another exposure being displayed on the new exposure. So that's the ghosting artifact. More sensitive to noise and scatter. See our added potential sources of noise from mechanical, optical, and computer components. So this wraps up our video for computed radiography. Computer radiography was widely used in the 90s, the 2000s, and in 2010s. Digital radiography is now almost exclusively used in all imaging departments. In the next video, we'll discuss DR and why it's the ubiquitous technology in imaging today.